okay, to give me the opportunity to be here and to present part of the work that I'm doing with my collaborator at the Italian Institute of Technology in Genoa. A word that maybe has not been mentioned so many times today, quantum. So I think that you are agreed that anyway quantum technology are going to revolutionize many photonics research. So, and obviously also microscopy, optical microscopy, and fluorescent microscopy. So today what I want to show you is how one of these quantum device, specifically a single photon detector array, can trigger what I consider can be a new generation of laser scanning microscopy. So briefly, I will talk about this BrightEyes project. Okay, so I mentioned about laser scanning microscopy, and we saw already many talks using such a system. And I can say that maybe also together with the wide field architecture, laser scanning microscopy is one of the most popular microscopy architecture in life science. The reason of this popularity, to my opinion, is that first it can be combined with fluorescence, giving this ability to be sensitive and to be specific at the molecular level. And then also because it can be combined with many other advanced microscopy techniques. So just to mention a few, with confocal microscopy, I'm sure that everybody of you know about that thanks to confocal microscopy, you can achieve three-dimensional imaging inside your sample. Or today we saw a beautiful talk about two-photon excitation microscopy, in which you can use this excitation regime to go deeper in your sample. Or we can mention about STED microscopy, the previous talk. So combining laser scanning microscope with the STED principle, you can achieve, in principle, unlimited spatial resolution. Fluorescent lifetime imaging, Alberto already mentioned, which is fundamental for functional imaging. And I can mention many, many more. So anyway, at the end of the story, what you have is a microscope that provides you a unique combination of tunable spatial and temporal characteristics: spatial resolution, spatial range, how deep, how wide I can make imaging, temporal range, how long I can make imaging, temporal resolution, how fast I can make imaging, and information contents, very, very important. So we are not here to make only nice, pretty images, but we want to get information about our sample. So, so it's clear it can be a sort of, seems to be a sort of perfect instrument. But when I start work at IT, I thought, okay, it's so perfect, this system. And the answer was no, to our opinion. So there is a fundamental limitation in current laser scanning microscopy. And I will try to explain you which is this fundamental limitation and how we can solve this limitation. So I then need to little bit to be back introducing again how a laser scanning microscope works. I will go really fast because I'm sure that many of you already know. So anyway, basically you have a laser, you have an objective lens, and you use this objective lens to focus your laser beam in a specific position of your sample. Typically you generate a diffraction limited spot. So all the molecules, so I'm talking about fluorescence microscope, all the fluorophore inside this region, this probing region, will be excited and will emit light that is collected by the same objective lenses, pass through a series of lenses, and then it passes the dichroic mirror because I want to separate fluorescence from the excitation, and then is focused by the tube lens in the image plane of the microscope. So here, typically what you have a photomultiplier. So, and what a photomultiplier is doing is integrate all the light that arrive from that you have in your image plane. But look, here I have an image, and I'm using a single point detector. So I have an images with a spatial distribution, and I completely cancel out this information because I have a single point detector. Okay, so I have an image, but I integrated the signal across the space. Well, something wrong. Then what happened? Typically, my signal that provides, it's a very fast detector, can be gigahertz, so in principle really fast. But then what I have a data acquisition system that integrates across the time. So again, another integration. I integrate across the space, and then integrate across the time. I have an image, and I have an image that in principle changes in time, because fluorescence is dynamics. So molecules are moving, everything is changing, so the signal is also changing. I have an image that changes in time and end up with a single intensity value. So spatial and temporal information, where they are gone. They disappear because I integrated them. So okay, that's a scan. That's an image now describing the laser scanning microscopy in terms of imaging. So what happened that I scan my probing region across the sample, and then I end up with digital images. But anyway, for each probing region, I give you a single intensity value. So there is something wrong here. So for people that came from single molecule world, that's obvious. If you start to make averaging, you are losing information. Here is the same. I'm averaging light. I'm averaging photon across the time and space. So that's a problem, at least for us. That means that there are information that are lost from the microscope. So obviously, you can circumvent this problem. There are strategies. So for example, if I substitute my photomultiplier with a single photon detector, I can sampling the fluorescent light photon by photon. So I can preserve the temporal distribution of the photon, how the photon arrived to my image plane. But what about the spatial information? Again, that's a single element detector. I'm losing this spatial information. Okay, I can use a camera. Super nice. That's a pixelated detector. I can make an image of my probing region. But what about the time? These are really fast. These are really slow. They cannot sampling the signal at the photon level and then by preserving the temporal information. So I have solution, but they are only partial. So that means that, so what we thought, okay, we would like to solve this problem. How we can do to solve this problem? So unfortunately, as a lab, we are expert in microscopy, but we was not expert in detector. So we approached the Polytechnic of Milan, and we sit together to design the perfect detector that can solve this limitation. And in particular, we designed the first single photon detector array. So I will go a little bit more into detail, designed specifically to solve this limitation that I hope that I convinced you that exists in a conventional laser scanning microscope. I don't want to go into the details of this kind of detector, but just I want to tell a few things which are important to understand the next of the talk. So basically, that's a single photon detector. So that means that that's a matrix, sorry. So it's a very small matrix, only 5 by 5 elements. So because if you think a probing region is only a few hundreds of nanometers inside, so you don't need a really big camera to make imaging of that. So you need just 5 by 5 element. And very important, every of these elements is a single photon detector, and is completely independent from the other one. So every time that a photon reaches one of these elements, there is a digital signal that is fired and go to my data acquisition card. So basically, this signal has a precision of a few hundred picoseconds, very high precision. So spatial information, I can sample photon in space. I know where the photon arrived. I preserve the image of my probing region. And I also preserve the time, because I know exactly at which time the photon arrived to my detector with a precision of 100 picoseconds. I can skip this slide, but anyway, just to tell you that for the first prototype that we started to work in 2019, there was many development, and nowadays there is also a commercial version of this detector. Also because this SPAD array, because these are single photon average diode array detector, was a well-known technology. So what we do, we simply sit together with the Polytechnic of Milan and we design the one that is specifically good for our application. So, but now, as I told you, I have a way to collect fluorescent light photon by photon. So the detector provides me the signal photon by photon, but I need also to register this signal photon by photon. And specifically what I need to do is to use a data acquisition card that is called time tagging. So basically, it's this data acquisition receive, every time that a photon is collected by one element of the detector, it receives a digital signal that is able to store with a certain, with a tag time, with a temporal tag of the order of picosecond resolution, as I told you before. But it's also able to collect all the other synchronization signals from my system. For example, when the beam is moving thanks to the Galvo system, or the many other synchronization signals that I have with my microscope. So at the end of the story, I do not build an image, but I build a list of events. By processing this list of events, I can get a list of photons, and every photon bring with him a lot of information, both in the spatial domain and in temporal domain. For example, for each photon, I know from which region is coming from my sample, in which region of my detection has been collected, the time from the delay, for example, for the beginning of the experiment, the delay from the changes of the pixel, the delay from the synchronization laser, and so on. So I'm not anymore any images, but I have a list of photons. So I'm collecting the data photon by photon. Photon resolved imaging or single photon imaging. Obviously, if I have this data set, I can be back to the normal imaging. I'm just making histogram. But obviously, I cannot do the other way around. When I have an image, if I use conventional imaging, I cannot be back to the list of photos. So the beauty is that I can go in one direction. I can always be back to the normal, to conventional imaging, but I cannot do, obviously, the other way around. So when I have all this information, then we put in our microscope, and we came out that basically we can improve almost any characteristic of the laser scanning microscope. For a question of time, obviously, I will not mention, I will not talk about all of them, but I just want to show you a few examples that maybe are good in the context of this conference. So, of this workshop. So first of all, I will show you how exploring the new spatial information provided by the detector, I can improve the spatial resolution of the microscope, specifically the spatial resolution of a confocal laser microscope. So in this case, I've discarded temporal information. At this moment, I don't care. I just integrate across the temporal dimension, but I preserve where the photon arrive, where the photon come from the sample, and where the photon arrive into the detector. So here is an example now how the image is built. So basically, for each position of my sample, here I mimic a scanning, I collect what we call a microimage. So that's the image of the probing region. But you can see this data set from a different point of view. So if you think that every element of the SPAD array, of the detector array, is like a pinhole, it's like at the same time that I'm making the scanning, I build up 25 images, because here it's 5 by 5 elements. So I can see in this way, so that's the image of my probing region where I focus my light, or I can see the same data set as 25 images, 5 by 5 images, the scanned image, collected from a slightly different point of view, because the detector is placed in a different position. And specifically, oops, I lost one slide. Okay, yeah. So anyway, what happened is that basically, sorry. Yeah, much better. So basically, I have 25 images, as I told you, and every image is characterized by its own Poinsperry function, and the Poinsperry function is pretty similar. So let's say it's a Gaussian function, especially for the pixel close to the central one. And what is changed is basically in the position, because I'm collecting the light from a slightly different position. So at the end of the story, I have 25 images of the same sample collected from a slightly different point of view with similar Poinsperry function. And what I can do is to apply what is called pixel assignment. So it's a very basic and fast algorithm for which I take the 25 images, I correlate each other, and I sum them up. So by doing this simple operation that can be done in real time, so I end up with a Poinsperry function that is square root 2, is almost twice smaller than the Poinsperry function of a conventional microscope. So twice the resolution, basically for free. Just simply change the detector of the microscope. Here are a few examples. Unfortunately, yeah, the projection is changing quite a lot, what I can see here from my video. So anyway, that's a tubulin network. So that's a conventional confocal microscope in which typically you use a pinhole to improve the resolution, but when you have a pinhole, you reject a lot of light. So here is an intensity profile along this direction. So basically, you cannot really distinguish that there are some tubulin structure. Here is if I open the pinhole, so I collect all the light. So because one particularity of this detector, since it's a big detector, is collect all the light that is coming from the sample. So, and thereby, okay, I collect more light. As you see, there is an intensity increase. That's the intensity profile along this direction, but the resolution degrades because I'm losing some sort of spatial information. If I apply pixel assignment, the approach that I told you before, here you can see almost a nice improvement in resolution, but you can better see here that you clearly see these two peaks. That means that the resolution improved because now I can distinguish two features in my sample. We are a group of computer scientists, so we apply also more fancy algorithm based on the convolution where you can further improve the contrast of your images. So other example, because what is very important of this technique, that it's a sort of technique that is almost for free in the sense that you don't have to change nothing in your sample. It's okay for tubulin, obviously, but it's okay for any other structure. That's, for example, the distribution of chromatin inside the nucleus. That's maybe a little bit more in the context of these conferences, so you can better see how you can better reveal the neuron spine in your sample. And another thing that's important can be obviously combined with two-photon excitation microscopy. Here is an enhancement in resolution that you have when you apply pixel assignment. It's called image scanning microscopy because you do an image for each scanning position of the sample, and that's the conventional non-scanned imaging. So the resolution improvement is quite big. So as I told you before I was just discarding the temporal information, but that's an information that I have and I want to use it. In this context, I will show you an application in which I'm using the temporal information to measure the photon arrival time with respect to a pulse laser, which is the information that you need to measure what is called the fluorescent lifetime of your molecule, and thereby adding this sort of functional information to your measurement, because by the fluorescent lifetime measurement, you can understand, for example, the microenvironment of your probe, you can understand some interaction of your probe. There was one limitation when we started this project, the fact that we need to collect this signal from 25 elements, now 49, and at the moment on the market, if you want to do this operation, you need a lot of money. Really, really a lot, because you don't have a single card to do this operation, this time tagging data acquisition, but you need to buy, I mean, typically it's 8 channels, so you need 49, so you need a lot of this card, and it's a lot of money. So we decided internally to develop our time tagging data acquisition system. I'm just telling you this, I don't want to go into detail, but just because it's an open source project. So if you are interested to do lifetime with a SPAD array, but also without a SPAD array, you can contact us and we can save money. Okay, so here, as I told you, we can now measure the fluorescent lifetime because I collect photon one by one, and I can assign a temporal information to the photon, and I can use this temporal information to calculate the lifetime. So that's an image that I showed you before, a tubulin. You can clearly see that by taking advantage of the spatial information, I can improve the resolution. But more important, I can also tell you, I can provide you the map of the lifetime of this sample. This is not so much interesting because this was a fixed sample in tubulin, so basically from the fluorescent lifetime, I don't gain any real information about the sample. That's another sample, another example in which I have a live sample in which we was using a polarity sensitivity membrane probe, the ANEP, which is able to tell if I have an order of my lipid membrane or they are disordered. So, and they can clearly see the difference that you have in lifetime. So this is the color-coded lifetime. If you have the inner vesicle and while the lipid into the membrane that show an ordered phase. So in this case, the lifetime is used to understand the order of the lipid in my membrane. Together with super resolution, because as I showed you before, by using the spatial information, you can gain in resolution. That's another example we try to understand, we can try to understand using the lifetime, the state of an ion channel, when it's open and when it's closed. So it's again, it's a sort of functional information. Everything is live, obviously. Yeah, I think that I have time for another example. Yeah. So this is another example in which we are interested on the dynamic of a molecule, of a particle or a single molecule. In this case, again, we use both the spatial and temporal information that basically can be achieved by our SPAD array detector. And we combine this detector with the fluorescent fluctuation spectroscopy. So if you are interested on a very fast dynamic, unfortunately doing a raster scanning does not provide you enough speed. So we saw many talk about that highlight this problem. But there is a technique that is called fluorescent fluctuation spectroscopy, which is based on a laser scanning microscope, obviously, which is able to give you, that allow you to access to dynamics that are faster than any other microscopy technique. So the basic idea is that now I park my beam in a position of my sample, and then the molecule passing through this probing region of my sample, they generate some intensity fluctuation. So obviously this fluctuation will be faster if the molecule diffuses faster. So, but if I analyze such a fluctuation, I can understand, for example, the dynamics, the diffusion coefficient of of my molecule. In the conventional microscope, I have a single intensity value, I just showed you before, but now that I have a sputter ray detector, basically I can do almost imaging of this particle diffusing across my detection volume. And from another point of view, I can record 25 different intensity trace. Every intensity trace is associated to a specific position inside my probing region. I can obviously analyze this hyperdimensional data set in many different ways, so that's what we do in collaboration with many other groups. Today I want just to show a very easy and quite intuitive way to analyze the data, which is what is called diffusion law or spot variation FCS, fluorescent correlation spectroscopy. Since I can collect the light from the 25 element at the same time, what I can do, I can analyze the data only in subset of this position. So if I take, for example, the central element, or I take the 3 by 3, or I take the 5 by 5, basically what I end up is 3 different, let's say, detection volume with increasing size. And there is a study that is called the diffusion law. If you plot the transit time, so the time that the molecule spend to cross the probing region as a function of the size of the probing region, you can tell much more about the kind of mobility that you have of your molecule. For example, you can distinguish between free diffusion if this curve, that is the transit time as a function of the detection volume, pass through the intersect of the y-axis. If the intersect is positive, you have a completely different modality that is microdomain. So you have sort of constraint. Your molecule is free diffusing in a region and then jump into another one. Or you have, meshwork, and that's a negative intercept. While if you have a positive intercept, it's microdomain, which means that your molecule is binding to some specific region and then is releasing. So anyway, you can understand much more from a single measurement. So here is just an example. That's a very stupid example because it's simply a molecule diffusing in water, and you can see if you do the diffusion law analysis, this is passing to the 0 that tell you that is free diffusing. Clearly, that's not what we are interested in real life, so you want to, for example, understand how a protein like DEC is diffusing inside the cytoplasm or inside the nucleus of your cell. So, for example, here you can see that when the DEC protein that is expressed that is conjugated with the GFP is into the cytoplasm, you have a free diffusion, while when you are in the nucleus, clearly the environment is much more complex, and then you have a sort of microdomain mobility. So with a single measurement, I cannot tell you anymore only how fast the molecule is diffusing, but how the molecule is diffusing, which kind of mobility the molecule is doing. That's another example in which we use the same technique to understand, for example, condensate in a cell. So that's our stress granule. So the mobility of the molecule, in this case, was the GFP G3BP1, that is a molecule that is associated to this cluster, this aggregate, is changing after the inducing a stress to the cell. So the same cell, living cell, we can monitor before the stress, which show a specific mobility. After the stress, the mobility is changing. Okay, obviously we can combine this information with the lifetime, and I want just to go really fast to the one last example, which is, fluorescence correlation spectroscopy, fluorescence fluctuation spectroscopy is a wonderful technique, but it's an ensemble technique, again. So you try to understand how a molecule generally behaves. So, but you would like to be interested to understand how a single molecule effectively behaves. And that's what single particle tracking is doing. As I told you, basically this camera, this sputter ray, is able to make an imaging of the probing region. So you can see the molecule that is diffusing in and out of my probing region. So I can localize where is the molecule, basically in X and Y inside this small region. I can do the same for the axial position, because if I induce some astigmatism, the signature of my camera will be different according if the molecule is in the down part or in the upper part. So I can basically do tracking, single molecule tracking inside the field of view of my probing region. But unfortunately, this field of view is really small because, as I told you, it's diffraction limited. It's only 200 by 200 nanometer. But don't forget that that system is based on a laser scanning microscope. I can move my beam, and I can move the beam basically in real time. So similar to what I showed in the previous talk, I don't have a deterministic pattern in this case, but I can every time using a feedback loop to change the position of my probing region, use the galvo mirror or other devices in order to follow the molecule. So basically like a sweet spot, like an actor in the stage. So I'm moving and there is a light that follows me. So here is just an example. That's not a molecule. We are working our goal is to work with a single molecule. That's a particle. It's a lysosome. In this case, the particle moving. In this case, is moving along a tubulin. So the one that you saw in the back is a simple image that you collect with a laser scanning microscope, and then you start to track a particle, and as you can see, you can follow it that is basically momoving along the tubulin. The beauty is that the camera has no frame rate, so in principle, the temporal resolution of this system is limited only by the signal-to-noise ratio, how many photons I can collect. The other beauty is that in principle, also the field of view is unlimited, so just depend by the field of view of your microscope, and it's 3D. So for example, here you can see the movement that looks like a bidimensional movement, but that's not true because the particle is moving along all the three directions. So I want us to conclude, and I hope that I was able to convince you that if I introduce a SPAD array detector, a single photon avalanche diode array detector in a laser scanning microscope, I can open to new perspective. I can open to a new paradigm because now I collect light photon by photon. And what I show you is just the tip of the iceberg because many other projects are running in the lab. And hopefully, I'm sure that also many other groups will come out with some new idea because now we open a really two new dimensions, spatial and temporal dimension in your data set. And obviously, I'm sure that many people will come with some new idea. Another thing that I'm really proud and I want to stress is that we think that that can be really the future, and the future, I'm sure that I hope that company will follow us, but maybe there is no time in the sense that when a technology is ready, it will be nice having in the lab immediately. So everything that I show you is, most of the stuff are released as an open source project. So not only the time tagging system, but also the architecture. So we provide you we can provide the CAD draw to build up a single photon microscope in your lab, and also the controlling software, because obviously you can imagine that controlling and analysis software, you can imagine that a big part of this project is also we achieved thanks also to a good software to control everything and to acquire all our data. Finally, I want to thanks, I want to thanks. I want to absolutely thanks all my group. We are hiring, by the way. I want to thanks all the great collaborators from the Italian Institute of Technology, and in particular the group of Alberto Diastro. I want to thank the company, and I want to thank the fund, because otherwise I would be not here. Oh, especially if they are not there. So.
Super.